Hello everyone. Today we will do two-level three-factor DOE, and as opposed to last week where we did two-level two-factor DOE, two-level three-factor DOE is going to give us 8 experiments. We will have 8 experiments, and I will do only one today, one factor on paper, but please do check the DOE Lecture 2 Excel file, XS file in the Blackboard. So you can have the details of the rest of this analysis. So let's do an example, to start with an example. And the example is going to be epoxy curing, right? So then the goal of this is to find the best epoxy curing conditions. Okay, so to do this, we have 3 factors. We have identified 3 factors, okay? And these 3 factors are: A is the cure temperature. Okay. B is the epoxy percentage. Okay, so that means that how much epoxy that you're going to put. And C is the epoxy type. Right, and you can imagine that for a real DOE that you work in a factory, you could work with more than 3 factors. You can go up to 100 factors, you know, and then you'll have special software that will help you to do this type of analysis. But today we will just stick with 2 levels and 3 factors. So since I'm only doing 2 levels, right, so that means that I will have a minimum level, which I'll designate or code as minus, and I will have a maximum, right, which I will designate with plus. And usually these are again really determined by the physical constraints or the budget constraints, or really what you can do. So for example, the minimum temperature in here is going to be 160 Celsius and maximum going to be 180 Celsius. So it might be possible that the epoxy is going to get damaged after 180, or it's not going to start curing before 160, but there's a happy medium between 160 and 180, and we just don't know what that value is, so the DOE is going to tell us what is that. Similarly, the minimum cure epoxy percentage was 20%, and the maximum epoxy percentage was 40%. Again, the DOE is going to tell us what is the best between these two. And there's 2 types of epoxies, K type and L type, and you can imagine these are our 2 levels, right? And this is our 3 factors. Okay, so that's basically makes a 2-level 3-factor DOE. Okay, so what the DOE is going to tell us, right, based on this experiments, okay, it's going to be 1, largest effect. In other words, whether cure temperature A, epoxy percentage B, or epoxy type C affects the results the most, right, as well as whether changing one will affect the effect of the other. So that means that will there be effects of AB interaction, right, AC interaction, BC interaction as well as ABC interaction. So with this way, you'll be able to tell if changing one of these variables also affects the effect of the other one. And based on these interactions, right, we will be able to model and optimize the curing. Okay, you can imagine that at the end of each of these experiments, you'll be doing some sort of like a test, maybe a pulling test to figure out what is the maximum force required to pull apart the epoxy pieces, right? And then you'll be able to determine which one is curing the system the best. Okay, so let's go to the next page and write our experimental table. Okay, our experimental table was that the run, okay, was number 1, 2, 3, 4, 5, 6, 7, 8, correct? So we have 8 corners, right? So that means that we are doing 2-level, right? And 3-factor DOE, and that's going to give us 8 experiments, right? And if I were to represent this in a graphical form, right, you'll see that we will actually have a cube that looks like something like this. Okay, so it doesn't look exactly like a cube, but you got the idea. So one of our axes here, C, right? One of our axes here is A, and one of our axes here is B. So in that sense, you can say that this 0, 0, 0 is going to be our center, right? That will be average of all the experiments that we have done. And if I were to write it in terms of ABC, I will say that this is my minus plus corner. That's going to be minus plus corner. That will be plus minus corner. This will be plus minus corner. This will be plus minus corner. This will be minus corner. This will be I already did that. This corner will be minus, and the final one right here is going to be plus corner, right? So that will be 8 experiments. And what you usually do is that you go ahead and measure these 8 runs independently, and you usually run each corner 2 or 3 times and take the average of all of them. Okay, so that way you'll be able to do more detailed statistics as well. So let's get on with it. So we had 8 runs, right? And we know what the corners are, and then factor A, right? So I'm gonna write it this way. So the factor A, right, was 160, 180, 160, 180, 160, 180, 160, and 180. Our B was, right, based on our standard table, was 20, 20, 20, 40, 40, 20, 20, 40, 40, right? And our C is then going to be 4 Ks and then 4 Ls. Okay. And you have done 2 trials, right? You have done trial number 1, and the results were 59, 74, 50, 69, 50, 81, 46, and 79. And you also did your trial number 2, right? And the trial number 2 gave you 61, 70, 58, 67, 54, 85, 44, and 81. Okay, so then your system response in that case is going to be Y, okay? And then the Y is basically going to be average of, for example, the 2 trials. So average of 59 and 61 is going to be 60. Similarly, the other ones will be 72, 54, 68, 52, 83, 45, and 80. And you can imagine that this type of experimental plan can be correct for anything, right? In this case, we are doing a curing of epoxy, but this could be things like crystal growth, production line in a factory, or selecting the best pump for the drainage of the sort of soil that you are using. Anything that can be done now is doable. Okay, so let's say an important point here, right, is usually if you see in here, this is a structured table. So what I mean is that when I'm looking for the effect of A, B, and C, right? You remember that I was going to do effect of A when A is plus, minus when A is minus. Similarly, when I'm looking at the effect of B, I'm going to do B plus minus B minus. And similarly, when I do this for C, I do when the C is plus, minus when C is minus. And this is a structure table in a sense that let's look at the cases when the C is minus, okay, so or C is plus, doesn't matter. Let me switch to color. So we have 1, 2, 3, and 4. I show them as red, right? And when the C is minus, let's put them in blue, and I have 1, 2, 3, 4 blue. So this is a balance table. In other words, when I look at the number of A and B that correspond to when C is plus or C is minus, I will find the equal number. For example, let's count the number of positive B's, which I will show them with green here. So positive B is going to be 40, right? So that will be 1. And that will be 2 here, right? That correspond to the when the C was plus, and when C is minus, which is the L type, then I will see that there's another 2 of B plus here. So if I were to look at the with magenta, that the B minuses, I'll see that there's 2 B minuses, and the C is plus, and I will have 2 B minuses when the C is minus. So in other words, when we look at the C plus, right, I'm gonna write it into this right corner here. When we have a C plus, we have an equal number of A pluses, A minuses, right, B pluses, and B minuses, so that means that you are only measuring the effect of C when it's plus on average. And when we do minus C minus, and I will have the equal number of A, B, plus and minuses, in other words, that this will only give me to, if it will allow me to measure the effect of C pretty easily. However, there's a caveat here. For example, if you do this experimental order, right? So I'm going to write this in here in red. If I were to look at my order of experiments, if I do a regular order, in other words, if I start with my run number 1 and run through first 4, right, I will see that I will do so that the C is plus in first 4 experiments. For example, if each experiment is taking, I'm going to make a small calculation here on the right, 6 hours, okay, and my warehouse where I'm doing my experiment is not temperature controlled, okay, and I am also on a accelerated timeline, right? So that means that when I do my experiments, I do 24 hours a day, 7 days a week, right? So that means that if I do my first 4 experiment, each one of them will be 6 hours. So that means that it will be 6, 12, 18, 24 hours, right? And say if my warehouse is not temperature controlled, right, that means that if next day starts snowing, right, that the temperature on the warehouse will be different when I'm doing my experiments when the C is minus, right? So that means that if I do follow this order exactly, that I might have things like the temperature of the room changing that will affect the results, and I wouldn't know if the results are affected by C or the changes in the temperature, which is also a, a factor that I did not consider, but it might affect the results. So the real here is what you should do to alleviate that, right? You should randomize the order. So even though the run number that we'll use in our tables will go through from 1 to 8, you should do like a random orders, for example, 6, 7, 2, 1, 4, 5, 3, and 8, for example. So I just made up numbers, but you can see that by doing so, that you'll randomize the findings, and you should randomize it each time. Therefore, any effects that might affect the results, so if the order of your experiments affects the outcomes, then you should randomize it every time to get rid of that effect, pretty much. Okay, so now I have my experimental setup. So what I will do is just to code these findings, right, and also write the interaction. So I'm going back to standard setup table, okay, so standard setup table, okay, and the standard table is going to say that we have 8 runs, okay, so it will be 1, 2, 3, 4, 5, 6, 7, 8, okay, and let's draw my lines here so that will be easier to deal with. 2, 3. So right now what I will do is write the table for each ABC factor that I'm using, as well as their interactions, okay? So the first one is factor A, and I'm just using a coded view. That means that I will be, instead of using real values, right, I will be -1, +1, -1, +1, -1, +1, minus 1, and plus 1. So for my factor b, I'll do the same thing, right? So it will be minus 1, plus 1, plus 1, minus 1, plus 1, plus 1. For my c, I will have minus 1, minus 1, and then plus 1, plus 1, plus 1, plus 1. Okay, so I realized that I was calling this C in this picture, I was calling this K as C plus and L is C minus. I apologize, it will be, the order is now switched. Oh, what is this? Order switched. Okay, but that's it. So now let's do the interaction. So I'm looking at the interaction of A and B. So I simply do minus 1 times minus 1 is going to be plus 1, right? And it will be similarly plus and minus is going to be minus. And I will keep doing it. So that will be minus 1, plus 1, plus 1, minus 1, plus 1. Similarly, when I look at the interaction of A and C, I'll see that this will be plus 1, minus 1, plus 1, minus 1, plus 1. Oh. Minus 1, plus 1, minus 1, and plus 1. Okay. Similarly, when I do BC, I'm gonna do plus 1, minus 1, minus 1, minus 1, minus 1, plus 1, and plus 1. And finally, I do ABC, right? And that will be that A times B times C, and that will be minus 1, plus 1, plus 1, minus 1, plus 1, minus 1, minus 1, plus 1. And my system response was then, I'm gonna write it separately here. It was 60, 72, 54, 68, 52, 83, 45, and 80. Okay, so let's call our effects here. Okay, and we're just going to do all the A minuses minus all the A pluses, all the A pluses minus A minuses, right? Divided by 2. Okay, so I'm just going to repeat the example for what we did last week, but you can go back to our lecture and figure out how these effects are calculated. Well, let's go all the A pluses, so it will be run 2, run 4, run 6, run 8, and that will be minus run number 1, run number 3, run number 5, and run number 7. So it will be A plus minus A minus, right? And that will give me the effect. If I do the same thing for A, if I do the same thing for B, C, A, B, and so on, I'll find that this will be minus 5, 1.5, 1.5, 10, 0, and 0.5. My average is going to be 64.25. Okay, that will be the average. Okay, So based on this interactions, right, I can do a couple of observations. Okay, let's do those observations and we will move on. So the first observation is A has the largest effect. Right, so without a doubt that the 23 is the largest effect in this. So that means that it has the largest effect on the curing bonding strength, okay? And the other thing that I can say is that there is some interaction of well, let's go one by one. So the B has a -5 effect. So that means that if I were to increase the curing temperature, right, from 160 to 180, then I'm going to get 23 of increase in my bonding strength, right? But if I increase or decrease my epoxy, increase my epoxy percentage from 20 to 40, that I will actually get a decline in my bonding strength, right? In other words, increasing my epoxy percentage, right, doesn't help me. In other words, if I change from epoxy type K to L, I'll see that my effect is only 1.5. So the effect of going and buying the epoxy type K or L has a limited effect in what I will do. In this case, I will probably go with the cheapest one to save budget, right? The other important thing is that the interactions are somewhat weak, except when we look at the interaction of A and C. That means that if I change the epoxy type, right, my curing temperature might change. In other words, that I will be looking for different curing temperatures for each epoxy type that might be different from each other. So that means that if, depending on what curing temperature that I select, it might change based on the epoxy type that I have. But in other interactions, if I look at A and B, that means that epoxy percentage and epoxy curing temperature has a minimal effect, and similarly the interaction between the epoxy percentage and epoxy type has no effect at all, and overall ABC don't affect each other that much. So that means that we are really looking for isolated effects of A, B, and C mostly, and then the A has the largest effect. So let's write that down in here. A is bigger than B, and that's bigger than C in terms of effects. So if I were to model this system then, right, using a polynomial, I will be looking at, so average here, let me make a note, the average here is alpha 0, right? So if I were to deal with this, what I would do is to model the system by figuring out my alphas, right? So then my alpha 0, we already said it's the average. Alpha 1 is going to be the effect of A divided by 2. Alpha 2 is going to be effect of B divided by 2. And all the way to alpha 1, 2, 3, 4, 5, 6, 7, right, is going to be effect of ABC divided by 2. So that the model will be, the system response model is going to be alpha 0 times A times alpha 1 plus B times alpha 2 plus C times alpha 3 plus AB times alpha 4 plus AC times alpha 5 plus BC times alpha 6, and finally ABC times alpha 7. So we can really model our systems, right, with this, and that will give us ways to optimize for different A, B, and C values that will maximize the system response. We will be looking through this in Excel, and with that we can figure it out. So before we move on, I would like to make a point about a center point. So as you can see, let's do this example in 2D. There we go. So here's your two factors, A and B, and you are measuring 1, 2, 3, and 4, right? And that's really your four corners, right? And without the center point, you'll see that your runs are going to be 1, 2, 3, and 4, right? And that will get you factor A and factor B, and that will be -1, +1, -1, +1, and that will be -1, -1, +1, +1. Sometimes you at the center point, okay, so that's without the center point. Okay, and with center point, you will have 5 runs, so that will be 1, 2, 3, 4, and 5. So it will be -1, +1, 0, -1, +1, and this will be -1, -1, 0. That will be +1, +1. So the importance here is that with the center point measurement, right? So without the center point, right, you have a linear model, right? That means that if you're going from A minus to A plus, right, you have a linear response. In other words, there's only way that your response is going to change between A minuses and A plus is going to be linear. If you added the center point, however, you will see that you can go from A minus, right, to a center measurement, right, which is going to be 0, and then you go to a plus, right. It will be a potentially nonlinear, right? And if you actually look at your system response equation here, it will be alpha 0 times, right, A times alpha 1 plus B times alpha 2, right, and plus AB times alpha 3. And you can see that this is a linear equation, right? So when you add a center point, right, let's say this is without center, and so your R with center, okay, is going to look like this: alpha 0 plus A times alpha 1 plus B times alpha 2 plus AB times alpha 3. Now you're adding a nonlinear term, right? So it's a second order term, A square B square alpha 4. Right? In other words, now you added a curvature to your system, right? And your responses can change, right, in 3D as opposed to be just 2D, right? So it's something to think about when you do center points in measurements. So, and you can increase this, right, more by adding center points for each corner as well as a center point measurement. And you can see that you can complicate your model with a much higher order polynomials by using center points. So as you learn, if you need to do more complex DOEs, and this is usually how complexity is added, is that you add more center points as well as you add more sort of corners and measurements as well as factors. Okay, so let's go back to our example. So what we want to know, right? We know that the effect of A was 23, right? Is the largest effect. Okay, so the question is it significant? Okay, how do we know that this is actually significant or not, right? So you can easily do that with the t-test. Okay, and let's say you have a low values, right, which is A minus, right? And if you go back to the table, right, let me go and find the A minus values, right, from the table, right? I'm not talking about this table because this table only has the averages. So I'm going to go back all the way here and figure out all the A minus values, right? And let's write them with magenta. I guess that's good, right? So all the A minus values, right, is going to be 59. Okay, then it's going to be 50. Okay, then it's going to be another 50 and 46. Okay, so in my trial number 2, it was 61, 58, 54, and 44. Okay, and I can similarly do the same thing for A minuses and the other ones, but we're just going to deal with A, effect of A here. And if I write this down now, I will see that my A low values were in order 59, 50, 50, 46, 61, 58, 54, and 44. And my A plus, similarly, if I go back to my table and read all the different trials that I did, right, it will be 74, 69, 81, 79, 70, 67, 85, and 81. And you can imagine if you did more trials, you'll just add to this list, right? So in each t-test, right, you'll see that whether if this is a parametric or non-parametric. So let's review what decisions that we have to make in a t-test. Okay, so we can ask a one-tailed versus two-tailed. Okay, you can also ask paired, non-paired, right? So in this case, we will say, for the sake of argument, we can say it is a two-tailed test, although I know that my effect is actually 23. That means that I know that it's going to be increased, right? And it can be selected as one-tailed, but in this case, I'm just going to be on the cautious side and say it's two-tailed, right? And if my system is paired or non-paired, means that if I use the same system, it usually is paired, and if I use two different systems, it's a non-paired. You can use both ways in this case. However, I'm gonna select that it's a paired comparison because I assume that I measured the same system when A and B are different. However, the other thinking might be that every time you make a sample, you break it. It might not be the same sample. It's also fair, but let's go with these two options for now. And if it's a pair test, and as you remember, I can define a difference D, okay, and I can simply go ahead and do 15, 19, 31, 33, 9, 31, and 37. Okay, so I can also write my D average was 23. No big surprise there, right? We know that the effect was 23. My standard deviation is 11.3. My standard error, right, is 11.3 divided by square root of 8, because I had 8 different measurements. That will give me 4. That means my t-score is going to be D divided by SD bar, and that's going to be 5.75. My T critical is, I'm just going to look from a table for two-tailed paired and with the degrees of freedom of 8, so that will be T8 95, right, for two-tailed, and that's going to be 2.3, so I'm going to say this is two-tailed. Okay, and in that case, I will say that my t-score, right, was larger than T critical, so that means that effect of A is significant. Right, and in here I must have said my H0, right, is that the D bar is 0 and my H alternate, right, is going to be D bar is not equal to 0. So statistically now I can tell that there is a measurable difference of 23, and that was significant using a t-test. So we will switch over to the Excel sheet and we'll go through the other effects and how to calculate everything else in Excel. So follow on to Excel.
Hello everyone. So we are back with the Excel sheet. So I've just made this Excel sheet similar to what we have done in our example. So I will just run you through quickly. I'll think the best way to do this is that as I'm going through, try to listen as much as you can. And if you get stuck or don't understand the point, you can just stop the video, go back and try to understand it again. So we had 3 variables, right? I have called them A, B, and C, right? So these are cure temperature, epoxy percentage, and epoxy type. I designated a minimum level, right? So because we are doing 2-level DOE, so the minimums for ABC were 160 Celsius, 20%, and K-type, and the maximum level for the ABC were 180, 40%, and L-type. So basically, showing here is the standard table format, right, for A, B, and C. And you can see that this is the standard run setup. And this will be the same for any 2-level 3-variable DOE. So you can copy paste this for anything that you'll be doing in the future using the same setup. And then I just carried over the pluses and minuses, mapped them to the measurements or the factors that we have in our certain system. And I can already see that these are not correct. So it's K-type, 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 and K-type here. And this will be L, 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 L. Okay, and now you assume that you have two trials, so you did the same experiments, right, for trial 1 and trial 2. And obviously, as we have mentioned that you won't usually do this in the same order, but let's assume that you have done this in order 7, 5, 4, and so on. So it's a randomized order. And then you're taking the average of these two, right? And then you're written the average value. So this is basically would be your experimental part. So if you were doing a DOE, this would have been the experimental part. However long or complex this experiments might have been, you'll end up with this table and with these experimental values. So from this on, you usually move over to a DOE software that you can analyze this data. However, we will do this in Excel and I will show you one by one how to set this up. This is a little similar to what we have done last week in Excel, but I will just go over it one more time. Okay, so this is just the experimental data, copy pasted. So we have 8 runs, factor A, factor B, and factor C. Again, I'm just doing this A and B, so let's copy paste this correctly. So this will be, okay. So now let's do the standard hand by hand calculation. So in this case, as you imagine, I'm going to do a coded DOE. That means that 160, 180s will become +1, -1s. 20 and 40% is going to become +1, -1s, and K and L is going to be coded as -1, +1 as well. So once you do this, and these +1 and -1s should be exactly the same with this table right there. And then I'll do interaction effects. So these are the main effect, and I will go to the interactions effects, and I'll write them AB, AC, BC, and ABC. And as you can see, AB is simply A times B at that given run, and you'll find this table. So now we have this table. I'm written the response, average response here. My alpha 0 is going to be the average of all the runs, and that will be 64.25. And then each effect is going to be calculated by mean value of all pluses. In this case, it will be run number 2, 4, 6, and 7 for A, and mean minus values, which will be the run numbers 1, 3, 5, and 7. And you take the difference between them and you simply do mean plus minus mean minus, and you'll get 23. If I do the same thing for B, you'll see the plus values, and here you will see the minus values, and I get the effect of -5. And I'll do the same thing for 1.5, 1.5, 10, 0, and 0.5. Okay, if I want to construct the model, then I will just find my alpha 0, alpha 1 values, and in here, let me call them alpha 1 to alpha 7, right? So this will be actually my alpha 1 to alpha 7 values, right? As you can see, this is simply the half of the effect of A, this is half of the effect of B, half of the effect of C, and so on. And as you can imagine, my alpha 0, right, is going to be my average, right? So here's are my 8 effects, so alpha 0, alpha 1 through alpha 7. I can do this in the matrix form, so this is the alternate setup, right? So I simply made my run again, right? So this will be A, B, and C, and AB. So I can set this up in a matrix form. The first one will be the identity matrix, and all the interactions and the main effects. And if you're not so sure how we have done this, please check the YouTube video that has been posted together with last week's um, um, lecture, and you'll be able to follow on. And I simplified the inverse of A, okay, and from the inverse of A, I simply do the matrix multiplication, and I come up with the same 7 or 8 alpha factors that I did. So let's check. Alpha 0 is 64.25. I'm checking it with the other version. It's the same. And then I'm looking for alpha 1, 11.5. I'm looking at the alpha 1, 11.5, and so on. And basically, we have found this 8 factors, alpha factors that will enable us to model our system. So when I model the system, I simply model it so that it will be, so I'm going to show with mouse, and then I will go to the equation. So I will do that it will be alpha 1 times alpha 0 plus alpha 1 times A, alpha 2 times B, then it will be alpha 3 times C, and then it will be then the alpha 4 times A times B, and so on. So you can look at this equation here. I'm doing the alpha 0 times C90, right? C90 right now is A, and then I am doing plus alpha 2 times, right, D90, which is, in this case, D90 is B, and so on and so forth. So it's basically, I just wrote the polynomial that we've been writing in our lecture part in Excel. So you just carried that over. It's a little bit tedious, but you'll have the Excel sheet, and I will encourage you to double check this. So the easiest way to double check, right, if I go and look at my run setup, right, I will know that if I make A minus 1, B minus 1, and C minus 1, my response should be 60. So let's check that out. I'll do A is minus 1, B is minus 1, and I check C is minus 1, and you can see that my equation gives me 60. I can check that out for plus, plus, plus as well. Let's check it for plus, plus, plus. So it will be 1, 1, and 1, and you'll see that it gets me 80. So what is the advantage of this then, modeling this in Excel? So let's say I would like to find a certain target that will get me get me ABC factors that will get me to a certain target. To do that, we will usually use a solver, okay? So I'm just going to go to the data folder and to solver, okay? I think we have done this last week, but I'm just going to do this for 3. So my objective is the equation that I'm solving. So it will be the F90, right? That will be my objective. And then I am changing the variable cells A, B, and C, okay? And you can set a couple of different things. I want to set either maximize it, minimize it, or go to a certain value. Let's say we want to solve this equation for a value of 77. That was the goal. And before we go on, okay, I would like to set up some constraints, right? Because we are doing a coded DOE, I basically said A can be between 1 and minus 1, B could be between 1 and minus 1, and C could be between 1 and minus 1. Okay, so I'm just going to delete the first one and re-add it, or let's delete the last one and re-add it. So the last one says E90, right, which is the factor C, is going to be bigger or equal to minus 1. So to add that, so let's delete that and let's add a new one. I'll just go in and click to E90, and I will say I will be either bigger or equal to minus 1 and say add. And from then on, you can add different constraints, okay? And I will just say then for a value of 77, let's solve. Our solver is telling me is that solver found a solution, okay, and all the conditions are satisfied, and I press OK. And in this case, if I choose a factor A 0.844, factor B is 1, and factor C is 0.47, then I will be able to achieve a 77 target value. So that means that you know then to get to the bonding strength of 77, you would basically adjust your temperature to 0.844, right? Adjust your epoxy percentage to 20%, right? Because it's +1. As you can see, we have found 0.947 for the factor C, but since we only had K-type and L-type versions, 0.97 doesn't really make too much sense. In that case, we will solve this for L-type only and see if we can find a and B values. I'm looking at the L-type that's designated as +1, right? Let's go to L-type and say change my constraint, right? Okay. Okay, so we can do that. So I can remove the constraints, right, on C, and I add a constraint that my C is going to be L-type. So I say it's equal to 1. I say okay, right? And then I try to put 77. Sorry. I then click this and say solve, and my say solver found a solution, okay? That means that to reach a bonding strength of 77 with the L-type epoxy, I will have to do a factor A is 0.671. It will come to a certain temperature, and it will come to a certain percentage of epoxy, and I should be able to hit. So basically, you successfully model your system. Okay, so that's the modeling bit. And now going back to these main effects, I want to see if the effect of 23 is significant or not. And to do that, we will do a t-test, okay? So I made a value here. So I'm basically going back to my trial data here, right? So here's my trial 1 and trial 2. And I do all the ones that show a minus A effect, right? And I made a bit here with these tables, so you can figure it out in Excel how I did that, but I basically go ahead and set up all the minus values for A, okay? And then I go ahead and set up all the plus values for A, okay? And everything is based on really this table that I'm highlighting here, but I made it easy for myself to make something in here. So it's basically the background work, so you don't have to worry about it too much. And based on that, I found the average of A minus and average of A plus, and these two values should be equal to the ones that we do in our table, and that gives you the effect of that. T-test, right, I found the difference of these two, so I get the differences all figured it out. Or with these, and I get my standard deviation, standard error, and the t-value, right, based on the example, and that gives us 5.75. It should be exactly the same. And I compared this against my t-critical, which is 2.3, right? It will be 8 degrees of freedom and T95. However, I realized that we only have 8 samples, so that will be degrees of freedom of 7. That will be this t value, t critical value, 2.365 as opposed to 2.306. Sorry for that. But then compare the t critical with the t value, that I will find that it is significant. And this is also a basically a plotted version of that. So you can see the plot. Here's the A minus effects and A plus effects, and that was significant. I can do the same thing with the effect of B. That also came out to be significant. I can see the effect of C was not significant, and effect of AB was not significant. Effect of AC was also not significant, so it was not an important interaction, and so on. So in that case, the only interactions that I found is that the effect of A and effect of B. So in other words, I can model the system only considering an effects of A and effects of B because they were the only measurable differences that we have got that were significant. So then I can maximize my system using my solver then and figure out by changing A and B, right? And A was the effect of A was the temperature, curing temperature, and effect of B was the epoxy percentage. And in that case, I can make the conclusion only thing that makes the difference in my system was the epoxy percentage as well as the curing temperature. And my epoxy type did not make any difference, and the epoxy percentage and cure temperature had no interaction with each other. So as you can see, by using t-test, I was able to nail down the important effects, and then I can make my conclusions based on that. Okay. So now with that, you can imagine that you can make your system response modeled easily. So I've also made a graph. So in here, you can see since our t-test found that the C has no bearing, that means that there was no C had no effect. So I set C to 1, which was L type. Then I varied A from -1 to 1, and I varied B from -1 to 1 at the resolution of 0.2. So each step is 0.2. And I basically calculated the effect system response with given C and changing A and B. And I plotted the system response, as you can see below here. And you can see as we switch the effect of A from -1 to 1, we get the biggest response change, right? So it goes from 52 to 80 in this case. And when I switch the B from -1 to 1, you can see that there's a negative effect as the system response decreases. So you can create a simple surface by varying two variables. We can also do the same thing for C is -1, and you can see the system response is a little bit different here, but we won't worry about that. So keep it 1. And this is basically how you model your system. If you add a center point at one point, that your curvature might change because now we have AB square terms, but in here this is a linear model, so we don't have any AB square terms. And this is how you can visualize your system.